Okay. Okay, now on this same page, 1015, AJ, could you read problem 9 to us?
That are the regions shown in the company figure.
Okay, can everyone locate the figure for 9? 9? Okay, continue, AJ.
Fill in the missing limits of integration.
Okay, so I got these 4 boxes on the board. Somebody tell me what to put in this box.
Well, that would be 2, and then the top one would be x squared.
We usually go from the lower to the upper limit. So let's draw the picture. This is the curve, agreed?
Yes.
Now what we're going to do is hold x constant, and we're going to find a strip in the y direction. So this strip is going to have a width, dx, but what is the limits of the y? What does the y vary from what? What's the y value here?
0.
And what's the y value on top?
X squared.
X squared. So please tell me what goes in this box.
0
0.
to x squared.
X squared. Okay, now when we finish that integration, we're going to add up all of these strips in this direction. And we're going to add all those strips up from left to right. So what are now the limits on the x integration?
0 to 2.
0 to 2. Okay, so we understand which direction the strips are going in. Okay. Now, let's do the complementary problem. We have f of xy, and now we're going to do the x integral first. So we have our 4 boxes again. This is part B. And now let's get our strips in the right place. I really encourage you to do these strips because it helps you to see what you're doing. So now what we're going to do is we're going to do the x integration first. So this is a strip that we're going to take. So now what is the left limit of that strip? So what we have in these boxes is y equals and y equals. We're going to go from one y to another y.
X squared to 2.
Well, we're integrating over x, so the x has to be disappeared. So
Square root of y.
yes, x is the square root of y. So this is the curve y equals x squared. Is it not also the curve square root of y equals x? True? So now, this point here, what is the y value of this point? If its x value is x, what's its y value?
Square root of y.
No. I got it backwards. If its y value is y, what's its x value?
X. Y squared.
Square root of y, right? Square root of y. So it has an x value which is the square root of y. And we're going to take this strip all the way to this point, so where do we stop this strip?
2.
At 2. So I should have x's here. So we're going to integrate from x equals the square root of y, and we're going to stop at x equals 2. So we're going to find the area in that horizontal strip. Now, after we get that, we're going to add up all such strips from top to bottom. So we're going to complete the integration in the y direction. So what are the limits of integration in the y direction?
0 to 4.
0 to 4, right, AJ? Because this top point has a x coordinate, a y coordinate x squared. So its point is 2, 4. So these go from 2 to 4. Okay, good. Okay, so we know how to do those. And what you do have to do is you have to solve for the value of x. So now I'm going to show you how, if you want, you can switch the order of integration. So the example that we're looking at is at the bottom of 1013 in the lower left. And I have the line y equals 2x, and we're going to use that line to give us a region between 0 and 1 on the x-axis. Okay. So if I want to know the area in this triangle, it's going to be a double integral. And the first thing I'm going to do is evaluate over x, evaluate over y, dy dx. Now, if it had some volume on the top of it, such as some canopy up in the sky, and so let's do it in 3 dimensions to show you. This is going out the x-axis. So this is our area in 3 dimensions. And up here in the sky, we've got some canopy that's going to be over that. So it's going to give us some volume. Canopy just has 3 sides with the footprint. Okay. So we're going to be enclosing some volume under our canopy. The question is how much volume. And the equation of the canopy is e to the x squared. The equation of the z, of the height of the canopy, is e to the x squared. So in order to find the volume, then the volume is going to be e to the x squared dy dx. So first, let's do it the wrong. Is it the wrong way or the right way? Yeah, let's do it the wrong way first. Suppose that you try to do the x integral first. And so you're going to do this x integral, and I guess it sort of gave it away. First, I just tell you that this line is x equals y over 2. That the equation of that line is x equals y over 2. So if you do the x integral, you're going to go from here to here. So what are the limits on the x integral going to be?
0 to 1.
No, it's this strip right here. What's on the left side of that strip?
Y over 2.
Y over 2. Read. What's on the right side is a 1. So these are the limits on the x integration. And now, if only we could do the integral e to the x squared, but this is an undoable integral. As simple as it looks, we can't do the integral e to the x squared. So we're stuck. However, you can reverse the order of integration. If you reverse the order of integration, then you find an integral that is doable. We're gonna do the y integration before we do the x integration. So we have e to the x squared, and when we do the y integration, that's just a constant, so that doesn't produce any complications. So now, what are the limits on the y integration? And now we're doing a vertical strip. So let's look at a vertical strip. So what's the lower limit on this vertical strip?
0.
0. And what's the upper limit?
2x.
2x. Read? So now we can do that integral very easily, and because the e to the x is just a constant, so we get 2x e to the x squared coming out, and now that's being done with x. Now, is that an integral that you can do? That's just e to the u du, isn't it? E to the u du? AJ, is that e to the u du?
Yes.
Okay, so the integral of that is just e to the u. So we traded an integral that we couldn't do in the x direction for one that we could do in the x direction if we reversed the strips that we're doing and we took the y integral ahead of the x integral. So the only thing to not miss is that when you switch from doing one integral first to the other, you have to resolve the equation of the limit. This equation of the limit was x equals y over 2. If we're going to reverse the order of integration, we now have to solve it for y. So what does y become? 2x. So when you reverse your order of integration, then you take the corresponding variable solved in your equation for the boundary of your region. So you switch limits, not in a naive way, but you switch limits by resolving the equation for the boundary for the other variable. Right? So let's have you do one. So page 1017, number 47. You don't have to, there's no function given, so you can't do it. But what you can do is reverse the order of integration and correctly ascertain the new limits. It might help to actually draw that footprint. You can go ahead and draw it if you want to, see what it looks like in the xy plane. X is going to go from 0 to 2, and y is going to go from 0 to the square root of x. So can everyone draw that footprint? Go ahead and draw it for me in the xy plane. What's the region of integration? Let's get a nice picture there. First, can everyone draw the curve y equals the square root of x? What does the curve y equals the square root of x look like?
It's a sideways top half parabola.
Are you trying to say it looks like that?
Yes.
It does. So we want to stop it out here at 2. So this is our region of integration. So Stuart, what are the new limits if we go in the other variable first, do the x first?
Y squared to 2.
Okay, the inner integral has y squared to 2. And the outer integral is?
0 to square root of 2.
Okay, that's well done. AJ, same? Hmm? we ready for a harder one?
That wasn't a harder one.
No, because now you have to actually evaluate the integral. 54 is done. Now you have to actually evaluate the integral in 54. Trouble?
Yep.
Did you get anything at all?
I'm stuck at trying to visualize what the graph looks like.
Cosine of x squared?
And it's a weird squiggly thing.
Um, It's gonna be a weird squiggly thing. That's probably sufficient. And just functionally integrate it. Okay? So you won't be able to integrate it without reversing the order of integration. Not easily, anyway. Well, no matter what the function looks like, all we really want to know is what the footprint looks like. We're able to draw the footprint, the XY plane part. The function itself is not too serious.
Nope.
Well, we can do it just by talking about it. The y value is going to go from 0 to 2. We agree to that?
Yes.
So the y value is going to go from 0 to 2. Because that's the outer integration, agreed? That's fixed. Now, the inner integral in 54 is going to obey the equation x equals y over 2. X equals y over 2, agreed? So we can either plot that directly, or we can just solve for y equals 2x, agreed?
Okay.
So this is involved in the integration as well. So we're going to have y go from 0 to x, and now let's be sure we have the right top to it. X is going to go from x is going to go from y over 2 to 1. So x is going to go from y over 2 to 1. So this is now the curve y equals 2x, or x equals y over 2, is this line. So it's the same line we had before. So this is the triangle, this is the footprint. So you have to draw the footprint. So now changing limits is done exactly like we did before, because they're the same limits, huh?
How did you get x equals 1?
I put in a 2 for y, because y goes from 0 to 2, doesn't it? That's fixed. Look at the outer integral. What's the
Okay.
range of y is fixed. So the fixed range of y fixes the range of x also.
I got sign 1.
That's right. AJ did it correctly. Want to put it on the board, AJ? Nice job.
So my
Nice job.
footprint looks different than yours. Well, I didn't make a triangle, I made the cosine curve.
The cosine curve is in the z direction. The cosine curve doesn't come into the footprint. So you did the mechanics right. You don't need that because you did the integration without the graph. Your graph is wrong
So these equations are set up entirely
by
on.
the limits. The footprint is set up by the limits. The footprint is not set up by the function of x and y. That just gives you the roof of the footprint.
Okay, I thought you had to make the footprint look kind of like the actual function.
No, the footprint is done by these 4 numbers.
Okay.
These 4 numbers give you the footprint. And the function x of y, it gives you the roof. So you get the volume above the footprint.
You get the 0 and 1 outside, and then
I
2x1.
have the integral 0 to 1 and the integral 0 to 2x.
0 to 2x or 2x to 1?
0 to 2x.
Zero to two x, the man's right.
Alright, so,
The man is right.
So do you still want me to put on the board?
Please, because we gotta get this demonstrably right. Okay, now, just get a little bit more practice, because apparently this is causing a problem. I just want on number 53 to use these four numbers and draw the footprint for me in the XY plane. Just draw the footprint in the XY plane for me, using those four numbers. It's nothing to do with the canopy. Fxy does not enter into the footprint. So can you draw the footprint on the whiteboard? Lynn, can you show them how to draw this footprint? In number 53.
Is it a half instead of a wall? Kind of? No?
Did I draw this one too?
Hmm?
Did I draw my one too?
That's Royston, yes. Is this y equals 4x? Draw for me y equals 4x. At least he can draw y equals 4x, right?
Well, how would you,
But let's do it. You've almost got it. Now, y equals 4x is one of the limits in y. What's the other limit in y? Now just keep it quiet. What's the other limit in y? Hmm? There it is. Can you draw that?
Oh,
Hi. So draw that. Bingo. A very good start, but not finished. First, y equals 4x is a straight line, so you can't have any curvature to it. And you have to finish it right. Stuart, could you explain the footprint to these other two classmates? Can you come over and have Stuart tell you what he's doing? Explain where it came from.
alright, so,
AJ, could you sort of lend an ear here?
I was got it there.
He's got it. Yeah, go.
alright, so upper is 4, the lower is 4x. So y equals 4 is one of them, y equals 4x was the other one. So here's y equals 4. And then there's y equals 4x.
I just got it right now.
Okay. Might be hope yet. So, on number 60, just show me the footprint. Just show me the footprint in 60. Hi. You can whiteboard it when you have something to whiteboard. win. I know you're gonna win. Yes, you win. Mhm. So shade the footprint. Okay, perfect. So once you have the footprint, then you can interchange the order of variables using the footprint to guide you, right? So now, in this footprint that Stuart has correctly drawn, we've been given that the first order of integration, well, say I give it to you. Since we've been given it this way, then the first order of integration would be a y. So this would be the integral of, just say, dy dx, okay? Let's write that down. Integral dy dx, no, it would be x dx dy. Over here, dx dy, we can leave that. So write dx dy. Now, double integrals, okay? Now, x is going to go from 0 to 1, true? No, we wanted y first. Let's draw a strip here. Draw a horizontal strip for me here. Okay. Now, in this strip, x is going to go from 0 to where? One minus y squared, true? And y is going to go from where to where? Okay. Now, if we interchange the order of integration, let's interchange the order of integration, put double integrals there. So now you can erase this one and draw a strip the other way. Okay. Now, in this, now y, this is your origin now. This is y equals 0 down here. Draw this line heavier so they see it. Y equals 0. So now, what's the range of y going to do? It's going to start where? 0, agreed? Now it's going to end at this point, but this point has to be expressed in terms of x. So you have to reverse this equation. Solve this equation for y. One minus x squared, agreed? So the upper limit is 1 minus x squared. Square root 1 minus x squared. And now what is the limit on x? 0 to 1 again. So you see this key step where you have to solve the given equation for the other variable when you change the limits. Okay, Jay? Good. Okay, so this will be the last one that we do on these footprints. Number 55. Let's draw the footprint. And after you draw the footprint, reverse the variables correctly. And it always helps to draw those strips. First draw a strip in the given way, label it, and then draw a strip in the opposing way, and create your labels by resolving the equation. So when you go to the whiteboard, you want to draw your footprint and then write the integral with the new limits once it's reversed. Nicely done. Hi. Okay. So we have two correct solutions over here. And it's time to turn the page.
I have one quick question
Yes,
before
sir.
we turn the page. So the problem I'm having is with the boundary, like whether it's I guess for lack of a better term, a roof or a wall on the graph. Does it just fall to the side of the first derivative? So if it's like a dx, it's it will be a wall, and then if it's like dx dy would be a wall, but dy dx would be a roof.
I think you're saying the right thing, yes. You mean a curve, a function,
This
and the footprint,
this thing here.
yeah.
I'm having an issue visualizing if it's can be either a top boundary or a side boundary.
Well, you'll have to see what it is that's being boundaried. If it's an X that's being boundaried, it's a vertical line. If it's a Y that's being boundaried, it's a horizontal line.
Okay.
Right. Okay, now, turning the page, we're going to do nothing new. So let's go to page 1018, jointly, please. Okay. Ten 18, 2 out of 3. 10 18.
Yeah.
Okay, good. Ready to go. Now, if we have rectangular coordinates, then our grid looks like this, and the natural area for our infinitesimal area is designated by boundaries which point to infinitesimal increases in our direction of our two variables. We look at the direction that the variable increases in. And x increases in this direction, and y increases in that direction. So this tells us how to draw our dx and dy. Now, if we want to use polar coordinates, because the problem works better in polar coordinates, then what I've drawn here is lines of constant theta. These are lines of constant theta. They're called rays, true? Now here, I'm going to draw lines of constant r. They're called circles, agreed? So you see that our natural area to take for dA is designated by boundaries, one of which is in the direction of increasing theta. So that goes this way, because that's the way theta is increasing. The other is in the direction of increasing r, so it goes directly out. So we align our little directional infinitesimals in the direction in which the variable is increasing. in other words, at right angles to a line of constant value. So we have a little directional infinitesimal that goes this way and a little infinitesimal that goes that way. So now we're going to then expand this infinitesimal region, dA, over the entire region. So let's look at what some of the regions can look like. First, the region can be bounded by two thetas. And it can have a upper curve of some R1 is some function 1 of theta, and this lower curve is R2 equals some other function of theta. So the region of our integration, the footprint, is a region that is between two constant rays with wiggly lines in the other direction, agreed? And this is the standard way to do it. We don't really much think of having R constant and wiggle theta. We just hold theta constant and wiggle R. This is what we do with polar coordinates. So this is the most common type of region that you'll have, where you have some region between two R curves that are bounded by lines of constant theta, or rays. And what you have is your little infinitesimal dA, which you integrate up. Now there's two ways you can integrate dA, and the first is that you can increase R alone. If you increase R alone, you get this strip, agreed? Then if you increase theta, then you get those strips next to it. However, you could just as easily have gone this way first. As you take theta from side to side, then you get a strip in this direction, and then you take strips next to it in that direction. So you have the same options as you do with x and y. You can do one of the variables before the other one, and that will give you a strip. And then you can propagate that strip according to the limits of the other. Now, since our two variables are R1 and R2, then what we're going to do is go from R1 to R2 as theta varies. So we will vary theta first, because going in the other direction, we're going to have constant R's and variable thetas, which we don't much work with because that's really messy. So this is the most common type of region that you will have, where this region is off of the origin and it's bounded between two R curves. However, the region can go all the way down to the origin. And if you look on page 1018, then you see region, simple polar region type B, where the lower curve actually goes down to the origin. So you essentially only have one boundary, the upper boundary, because the other boundary is 0, 0, true? Now the other thing is, if you take the bounding ray on top, beta, as called in here, and you go through a full circle with it, then it will meet up with the lower ray, agreed? And now what you have is an enclosed area. An enclosed area. And indeed, it's only bounded by one function, all the way from 0 to 2 pi, or from some starting angle alpha to alpha plus 2 pi. And so you can integrate that all the way around to get the entire area that's enclosed. Now the mechanics and techniques are done exactly as they are done for x and y. So there's going to be nothing new here. And the reason that you do this is because many functions are more easily evaluated in polar coordinates. For example, if I have this kind of a shape, and I want to evaluate it in xy coordinates, then I have dx dy, and then you have to evaluate between limits. And the limits are very hard, because the limits, as you know, are that x equals plus or minus the square root of 1 minus y squared. So those are strange limits. Y equals plus or minus x squared. Now, if you want to do this in polar coordinates, then the equation of this curve is r equals a. And all you do is evaluate it between 0 and 2 pi. And since r is a constant, it comes out of the integral. So which coordinate system is the area of the circle easier to evaluate in polar coordinates or Cartesian coordinates? It's the polar coordinates. And the same is true of many other such curves, particularly rose petals and carteroids and all those other classic shapes. You definitely want to be in polar coordinates. So the thing to realize is what is indeed the expression for dA in polar coordinates. Well, you might naively think that this side was of length dr, and this side was of length d theta. Well, that is close, but doesn't win. First of all, you need an area, which means you have to multiply a length times a length. And theta is just a number, it's an angle. So you don't even have the correct dimensions. So let's go back and ask you about our circle again. If you have a circle, and it's of radius r, and this is the angle theta, then what is this distance out here?
ARO.
R theta, true? Now, if you have a circle, and this is an angle beta, and this is a distance r, what is this distance? R beta, agreed? Now, if you have a circle, and you have an angle d theta, then, and this is r, what is this distance? R d theta, agreed? Okay, so now let's go back to our region that we want to evaluate, and we want to evaluate between these two regions, so we're going to take this to be our dA. Now, this is not quite a rectangle, because these rays, they're straight, agreed? But the other sides, are they not parts of a circle? They're curved. So if this is the point r theta, then this is the point r plus dr and theta plus d theta over here. So we have those 2 points. So we've gone out a distance dr, and we have rotated a distance d theta. So the length of this infinitesimal is indeed dr. But the length of this infinitesimal has to be understood by drawing these radii back down to the center. What is the angle inside here?
Theta.
D theta, agreed? What is the distance from the origin out to this point?
R.
R. So indeed, what is the length of this arrow?
R theta.
R d theta. So your little rectangular area in polar coordinates has side dr and r d theta. So dA in polar coordinates is equal to r dr d theta. dA in rectangular coordinates is equal to dx dy. So if you are solving your problem in polar coordinates, you start with dA, and then you immediately exchange dA for infinitesimals in your variables, one of which is dr, and the other of which is r d theta.
How come there aren't, I guess, 2 values of R? How come there aren't two values of R? If it's a block, then even though it's infinitesimal, the left hand of that block is a different distance from the origin than the right hand of the block.
It's not, because these are lines of circle, constant radius. That's what we take for dr. So this is also r, this is also r.
But the one to the right.
Oh, the one to the top is a little bit longer.
Right.
That's a little bit longer, but that's second order longer. To first order, it's still dr. Infinitesimally, the difference is real, except that these are infinitesimally small. So what he's saying is that this is really longer in the top than it is in the bottom. And that's true, but the increase in length is second order. It's of dr squared, if you will. So as we allow dr to go to 0, then it is dr squared, since it's a fraction, is negligible compared to dr. So it drops out. But you're right, technically speaking, that's always a little bit longer. So it's only valid when you actually go to the limit. And when you go to the limit, then this all shrinks down to just a point. And so there is no second line, there's only one line, so to speak. Okay, it's a good observation though. And that's handled in different ways by different kinds of hand waving in different approaches. And one of the ways to wave the hand is given on 1020. Where he takes his R line right in the middle of the circle. True? Okay? He says dr, he says the radius is in the middle of the rectangle. It's not at the top or the bottom. So then the lower one is a little shorter and the upper one's a little longer. So they average out. He takes his actual radius in the center, not at the lower limit as I did. So then you have this balancing act. But when you go to the limit, the center, the top, and the bottom all come to the same point anyway. So it's just a matter of waving hands. So on 1023, we have converting double integrals from rectangular to polar coordinates. And if you look at the equation in the middle of the page, it starts out as a function of x and y over dA, agreed? Now, if we stayed in x and y, dA would be dx dy, true? But we're not, we're converting to polar coordinates. So if you convert to polar coordinates, what does x become? R cosine theta. And what does y become?
R sine of theta.
And what does dA become?
R d theta.
That's right. Okay, so when you convert, that's how you make the conversion. Okay. So we are good to go. The assignment's in your hands now. And we've got these two sections to do. Saturday will be workshop. You can either come and we can do calculus, or you can just come and do calculus here, or you can come as a volunteer and give assistance to the algebra students. You're all invited to do either of those that you care to. And then we'll meet again next Monday. We're done.
Are we going to be getting into chapter 16?
Can't tell yet. 50-50 right now.
I think we can slow it down to one section tonight.
I know you can. Probably without even trying hard. Just have a lot of questions, a lot of puzzled hesitations.
Drawing pictures in my mind is not much.
curvatures on any surface is not my forte.
Stick figure is the bad.
Thanks for your help, sir.
Good night.
Good night.